So it's my pleasure to introduce Ladislav Skrbek to give today's webinar. So he's going to give us an overview on quantum turbulence in superfluid helium, and then some future perspectives of where the field will go next. So Ladik, when you're ready, please take it away.
Okay, thank you very much, Andrew. And first of all, I would like to thank you for this kind invitation to give this talk. And good afternoon to everyone from Prague. So I was asked to give more or less general talk, so I will try to keep that in mind. So I'm going to talk about quantum turbulence. And of course, quantum turbulence occurs in quantum fluids. And as we all know, quantum fluids are so called because physical properties of them cannot be explained by classical physics, but by quantum physics. And these quantum fluids, typical examples are isotopes of liquid helium at very low temperatures, but there are also other quantum fluids. And we are going to talk about quantum turbulence. And quantum turbulence can be defined loosely as the most general way of motion of a quantum fluid describing superfluidity. So quantum fluids, they differ from ordinary classical fluids, viscous fluids, in three important respects. So they display superfluidity at certain conditions. They, at finite temperature, display the two-fluid behavior, and also the circulation in quantum fluids is quantized, and it just contains the quantized vortices in it. So historically, quantum turbulence was first mentioned as a theoretical possibility by Richard Feynman in his famous article out of 1955. And experimentally, as we all know, everything started from the pioneering work of Joe Winen, and everything was described in the series of articles which are just listed here. But the term quantum turbulence as such was introduced later into the literature by Carlo Barenghi, who is in the audience. It was in his PhD thesis in 1982, and later it was also advertised by Russ Donnelly in a symposium which was dedicated to G.I. Taylor. And recently, we just decided, okay, maybe the time is ripe that we write a book about that. So the book appeared just recently, and it has a long history. Actually, with Carlo and Srini, with Katapalli Srinivasan, we had this in mind already more than maybe 15 years ago. But at that time, we decided maybe the time is not ripe yet, so we better organize a special issue of PNAS, and about a dozen of articles appeared in PNAS in 2014, and only later we started slowly to write this book. So, as I said, it is now possible to order it at Cambridge University Press, and the book has about 300 plus pages, and here is the content, which contains 13 different chapters. And I should add probably that both Carlo and myself, and as well as Srini, we had a pleasure to collaborate. And with Carlo, we even have been members of experimental groups of Joe Winen and Russ Donnelly. So it was our pleasure to dedicate the book to them. So it starts, of course, with preface and introduction, and then we go and describe what quantum fluids are and what are the main properties of them. Then we introduce quantized vortices, and then there's a long chapter about experimental methods. Some of them are just the same or similar as they are used in classical turbulence, but some of them are pretty special, and they are all described in this book also. Then we switch gears and talk about theoretical and numerical models. Then we go to proper experiments and describe transitions and steady-state turbulence, oscillatory turbulence, and then some special features of turbulence in superfluid helium-3b. Then we talk about spectra, structure functions, and also visualization via tracer particles of quantum turbulence, then about the decay, about regime of quantum turbulence. And that's basically what the book is all about. So Andrew asked me to advertise the books, which I did, and now we can go a little bit further. So what I want to do in this talk, I would like to remind a simple phenomenological description of quantum turbulence in helium-2 in virtue of well-developed phenomenology. And I mean, of course, I will use just the classical homogeneous and isotropic turbulence, three-dimensional turbulence in viscous fluids, which actually we published a few years ago together with co-authors as it's listed here. Then I would like to mention some peculiarities related to transition to quantum turbulence, and perhaps if I have time, some new results on spherical counterflow. So let me start. So what are the working fluids to study quantum turbulence? The most typical fluids are helium-4 and free helium-B. Free helium-A phase has not been used extensively to study any kind of quantum turbulence, so I will not consider it again. And I will not consider also atomic BEC condensates, 2D quantum turbulence, and some exotic working fluids which might occur in neutron stars or in heavy atomic nuclei and so on. So what we are going to talk about is for helium and free helium. So if we go down with temperature, we have normal helium-1 and normal liquid helium-3. And they are very different because normal liquid helium-1 has very low kinematic viscosity, while if you go close to superfluid transition in the case of helium-3b, it's a very viscous fluid, which has a viscosity which is comparable with that of air. And if we just go through the superfluid transition, we have a mixture of two fluids. It's an intimate mixture of two fluids. It's actually not a mixture. It's just because of kind of based on two fluid model of Landau and so on. And the circulation in helium-3 and helium-4, they are rather similar. They are of the order of 10 to minus 3 centimeters squared per second. But then if we go to the zero temperature limit, we are in pure superfluid turbulence, which is nothing else but a tangle of vortex lines. So at this point, I would like to clarify the terminology. By quantum turbulence, we mean just any turbulence in any quantum fluids. By superfluid turbulence, we mean a turbulence either in a superfluid component, or if we talk about zero temperature limit, it will be just the superfluid turbulence in this limit. I mean, in this limit, superfluid and quantum turbulence means exactly the same. And I would like to start with the energy spectrum. So this is just the spectral energy density. It is probably useful to remind what does it look like for classical homogeneous and isotropic turbulence in viscous fluids. So we actually drive the turbulence at some scale. The scale is here called M, and it might be, for example, a mesh of a grid if we drive the turbulence by a grid. And then the energy flows both ways in k-space to the left, but to the left it cannot go too far because there is no decay on the left, but it goes to the right. And to the right it goes via so-called Richardson cascade. So there is inertial range of scale with this famous Kolmogorov exponent. So it is proportional to k minus 5/3. And it goes through this Richardson cascade until it is dissipated at dissipation length scale, which from dimensional argument can be written as epsilon over nu cubed into power minus 1/4, where epsilon is the energy decay rate. So here it is dissipated by viscosity. And also because the eddies, which cannot be bigger than the size of the turbulent box, so there is no spectral energy density at smaller k vectors, which are larger than roughly 1/d. So if you want to let such a turbulence to decay, so there is a decay model which is rather easy to understand. But I mean, if this blue curve is how it looks like in steady state, and if you just stop the input and let it decay, so at some later time it will have this kind of form, and you can see that this just top, which is called just the peak where it is called energy containing length scale, and these are the most energetic eddies. So it grows until it reaches just the size of the box. And then the decay changes shape. And actually, the early decay in terms of energy goes as time into power minus 6/5. Vorticity goes as power into minus 11/10. But I mean, for us, it is more useful if we remember that the vorticity will just go like this, but energy goes as T to minus 2 in classical turbulence, and vorticity as T to minus 3/2 after just saturation of the energy containing length scale. So let us first, for the simplicity, consider just the simplest case. That means the case in the zero temperature limit. You know, this Richardson cascade in the zero temperature limit cannot operate the same way as it does in classical fluids. So we know that in classical fluids, everything is governed by Reynolds number, which is just the ratio of the size times characteristic velocity over kinematic viscosity. But we can actually define the superfluid Reynolds number, which is just the same by analogy, but the kinematic viscosity is replaced by the quantum of circulation. Or in analogy with just the classical dissipation scale, we can replace nu in dissipation scale, and we can define something which we call quantum length scale, which is epsilon over kappa cubed in power minus 1/4. And actually, this is the length scale, which is very important for quantum turbulence, for superfluid turbulence in zero temperature limit. Why? Because that's just where the superfluid Reynolds number is of order of unity. And the Richardson cascade cannot operate anymore. Because if you are on the left here, then you can actually use the classical-like picture. Because you may think about quantized vortices making kind of bundles or just big structures. And because of partial polarization, you may talk about large eddies. And everything looks more or less the same as in classical turbulence. So everything works until the granularity, so to speak, of quantum turbulence shows, and it just happens at the place where Reynolds number is of order of unity. But there is no dissipation there because the viscosity is not existent there. So there must be some further transport of turbulent energy down the scale, and it occurs via the Kelvin wave cascade. So it goes along individual vortex lines, and it goes in helium-4 until you reach the phonon irradiation, and in helium-3b until you reach, say, the saturation of the calorimetric states in the vortex cores. So I should add probably that at finite temperature, the situation is much more complex because there are two fluids and there is mutual friction and so on, and we will talk about that a little bit later. So what are these characteristic length scales in 3D and for simplicity and for helium turbulence in the t equals to 0 limit? So of course we have the turbulence inside some turbulence box. So that's the outer scale. So where the energy input usually goes on. And then from there is this Richardson cascade operating until we reach this mean intervortex distance or quantum length scale. And that's nothing else but just the mean distance between the quantized vortices. And as I said, the Richardson cascade cannot operate anymore, but Kelvin wave cascade can operate, and it goes onto the dissipation scale, which is in this case due to phonon irradiation. And of course, there are also smaller length scales because the size of the vortex core is roughly 1 angstrom in the case of helium-4. But these very, very small scales, they have nothing to do with turbulence, so we may forget about that. So experimentally, we can access these scales. For example, if we just try to visualize quantum turbulence, we can do that by particle tracking velocimetry, say using small flakes of frozen hydrogen or deuterium. And experimentally, we can cover some experimental length scale, which are of the order of tens of quantum length scales. And on the other side, we can go just to smaller length scale, which are just order of magnitude smaller than the quantum length scale. And if we do so, then we get different answers. So this is experimentally how we can do it. And if you ask a question, are you quantum or are you classical turbulence, your answer which you get from the flow is twofold. Depends on which length scale you ask. If you ask on classical length scale, you get a classical-like answer. So the probability density function of velocity distribution will be of the form like in this lower picture. On the other hand, if you ask this question at very small scale, then there is a clear difference, and the probability density function has these power law tails, and that's a clear signature of quantum turbulence. So let me say a few words about pure superfluid turbulence at zero temperature, how you can, for example, generate it. So this is a Lancaster way, how you generate quantum turbulence. And you have to do it at very low temperature, which is technically something like 0.2 millikelvin in helium-3b. And if you do that and you just move this grid, so then there are vortex rings going away from the grid and they merge and create quantum turbulence. And this quantum turbulence is then detected by wires. And how to detect it? You can detect it using so-called under-reflection in helium-3b. The principle is as follows. So this is the energy spectrum on helium-3, and because the energy spectrum changes if you just draw the same line in moving system of coordinates, so it's tilted. So if you now have a quasi-particle which moves and approaches a quantized vortex, then this quasi-particle becomes under-reflected and goes exactly back in his footsteps. And because of that, actually, if you have some quasi-particles, they can make it through through one side of the quantized vortex, but quasi-hole cannot do it on the other side of the vortex. So if you have such a moving wire and surrounded by some quantum turbulence, the quasi-particle dumpings is reduced by surrounding vortices, and you can measure the amount of quantized vortices in the vicinity of such a wire. And I would like now to step aside a little bit, and I may add that actually last summer with Yuri Sergeyev, we had closer look about a possibility of under-reflection in superfluid helium-4. And it seems that it is possible because you have minus rotons and plus rotons, and it doesn't matter that helium-4 is bosonic superfluid and helium-3 is fermionic superfluid. Still, under-reflection is possible. And in this paper, which is listed down here, you can read the details. But it is not just the theme of our talk today. So I just leave you with this. And if you are interested, you can ask or we can read the paper. Okay, but now I mean about the quantum turbulence in this very low temperature limit. So what's going on? First, you just drive it on the size of the mesh, as I have shown you. And if you drive it very, very little, then the quantum length scale is just of the same size as where you drive it. So because of that, there is just Vinen quantum turbulence. And the decay of the Vinen quantum turbulence goes as 1/T. That's the signature or fingerprint of Vinen turbulence, if you like. But if you actually increase the drive, that means there will be more quantized vortices. The quantum length scale will shift towards the right, just from the mesh right here. And what happens is that there is a Kolmogorov-like spectrum building up here, because there is a little bit of Richardson cascade here already. So there is a crossover. And if you drive it a bit more, that there is a quasi-classical Kolmogorov inertial range just appearing here. And then the decay should go, as I showed in the classical case, as T to minus 3 halves. I mean, the vortex light density goes as 1/T minus 3 halves. And that's indeed what has been seen in the experiment. So if you drive a little bit gentle, just gently, the quantum turbulence, you have the decay which is consistent with 1/T, but then there is a crossover, and you have just, instead of Vinen turbulence, the Kolmogorov turbulence, and the decay goes as T to minus 3 halves. And if you do a little bit of maths and you look a little bit more closely to that, everything actually works. And there is additional proof, because the Lancaster experiment was able not even to measure the vortex line density, but also the energy. And as I said before, the energy changes the decay from T2 minus 3/2 to T2 minus 2. And it has also been seen in this case of zero temperature limit. So how to characterize the Vinen turbulence and Kolmogorov turbulence? The Vinen turbulence is kind of featureless. So I used just this numerical simulation of Carlo Barengis and Andrew Bagali and of that group. So you see that Vinen turbulence, if you coarse grain it, it is featureless. But the Kolmogorov turbulence, I mean, like classical turbulence, there are intense vertical regions. So that's the difference. And the coarse grain superfluidity for Vinen and Kolmogorov turbulence are very different. And that's the main reason, difference between them. So now, if you compare classical two-dimensional homogeneous and isotopic turbulence and pure superfluid turbulence in the zero temperature limit. So what just is the message you can take home? The key point is that for classical turbulence in the unbounded state, there are only two length scales which you have to consider. And that's the length scale at which you drive the turbulence and the length scale, dissipation length scale, at which it dissipates. In superfluid turbulence, or if you wish, quantum turbulence in the zero temperature limit, there is, as I already introduced, an additional important scale, and namely the quantum length scale, which intervenes. And in this pure superfluid turbulence, cannot be considered, in contrast to the statement in the literature, as a simple prototype of turbulence. And I claim that despite the similarities, quantum turbulence is different and always more complex than the classical case, just because there is this extra scale which intervenes. So just although it is in the literature very often stated, I do not believe it's true, and I believe that the quantum turbulence is more complex than the classical one. So let me say a few words about transition to quantum turbulence. I mean, we recently wrote a perspective which will appear in PNAS. So transition to turbulence in classical fluids, it's a complicated process, as we all know. So it started with just the famous experiment of Osborne-Reynolds. And we know that if you do numerical simulations, so this is the way how turbulence just appears and gets excited and generated in the flow past a flat surface. And if you have some flow past, say, a sphere or cylinder, so we know that the transition to turbulence is pretty complicated. And what you can do, you can measure, for example, the drag coefficient and as a function of Reynolds number. And say, in the case of a sphere, you just see that there is a laminar flow, then there is a just kind of crossover. And also for sufficiently large Reynolds numbers, that is the drag crisis. I don't want to go into details. This is just to illustrate that the transition to quantum turbulence is complicated enough process in classical turbulence. But on the top of that transition to quantum turbulence, especially in the two-fluid nature, it's even more complex. Why? Because superfluid turbulence always involves quantized vortices. And the process of vortex nucleation is pretty complicated. These quantized vortices, they can appear spontaneously if you cool a sample of helium through TC using so-called Kibble-Zurek mechanism. But if you go to lower temperature, they should disappear. They would disappear if walls are absolutely flat, but they are never flat enough, especially in the case of helium-4. So there are always nice vortices. And actually, thanks to the famous work of Avshalom and Schwartz a long time ago, we can even estimate for certain geometries what the remnant quantized vorticity inside such a cavity or inside a sample of helium-3 would be. Vortex nucleation can be loosely divided into two different ways. So there is either intrinsic or extrinsic. Intrinsic means that you have a sample which is completely free of quantized vortices, and you create these quantized vortices by some object which moves very fast through superfluid, for example, some positive or negative ion, or by some really fast motion of some other objects, or by flow through very small orifice. But as I said, you always, almost always in practice, have a quantized vorticity. And there is extrinsic vortex nucleation. Sorry? Sorry?
I think there was just some background noise. I've muted the person.
Okay. So we have intrinsic and extrinsic nucleation, and this extrinsic nucleation is what takes place in most cases in practice. But in helium-3, if you are careful enough, you can have both intrinsic and extrinsic nucleation at the same time. Right. So the conceptually simplest case is just the zero temperature limit. But on the other hand, it is very difficult and nearly impossible just to repeat experiment of Osborne-Reynolds, say even in helium-4, in the zero temperature limit. At least I don't know about any such experiment which will be at least near to the accuracy and clarity and perfectness of Osborne-Reynolds experiments. So experimentally, it is the most difficult case. So that's why people usually use oscillating objects. And these oscillating objects, they are of very different size, very different shape, and they oscillate at various frequencies. And typically, these oscillating objects are grids, or these days, say, tuning forks, and so on. So using this tuning fork, we have been able just to observe in the zero temperature limit up to 3 critical velocities. And they are clearly seen in this picture. You see, this is the drag coefficient, which is measured as a peak velocity of this oscillating tuning fork. And you see the first critical velocity is just right here. And you can only see it at very low temperature, in the zero temperature limit almost. And the drag coefficient doesn't change, doesn't jump. And actually, it looks like at this first critical velocity, there are changes in frequency and like effective mass rises due to vortices which are probably pinned to the oscillator surface. And only if you go higher, there is the second critical velocity, and there is hysteresis usually, which is observed depending which way you measure it here. And this second critical velocity usually has been considered as a transition to turbulence. But I mean, in some cases, if you go to really, really very high peak velocities, and you can see here that with these little tuning forks, you can actually reach critical velocities up to few meters per second. There is a third critical velocity. And we believe that after this third critical velocity, there are large structures which start to develop in the wake, like in classical turbulence. So the first critical velocity actually means that there are little kind of vortex loops which move up and down and increase the effective mass of the object. The second critical velocity means that these little vortices, they start to twist and they reconnect, and there are free vortex loops, they fly away, and flying away, they just keep with them energy and momentum, and this is why you see increased drag force. And the third critical velocity, it is just the one which we are used to in classical turbulence. So we believe that in between these two critical vortices, between second and third, we have to deal with kind of a Vinen turbulence, which is featureless. But above this third critical velocity, we will probably deal with classical like Kolmogorov turbulence. So this oscillatory flow of quantum fluids at finite temperature should be actually considered also in connection with the normal fluid. And for that, it is useful if I remind what happens in oscillatory flow of viscous fluids. So the typical example is just the oscillating surface. And we see that if this blue one here is the amplitude, the red one is velocity, which trails by p/2. And because it's oscillatory flow, you don't use just one number like Reynolds number, but you need two of these numbers, for example, Stokes number and Reynolds number. And for the case of high-Stokes number oscillatory flows, you actually better use the Reynolds number, which is based on boundary layer thickness. And the boundary layer thickness is just the thickness at which, for example, the amplitude just goes down 1/t times. So we have this boundary layer Reynolds number. And if we are in the two-fluid regime of helium-2 in analogy for the normal fluid, we can define this boundary layer Reynolds number, but we would like to call it Donnelly number. And we introduced that because the Russ Donnelly was the first who used that already in 1958. And he tried to understand the motion of torsionally oscillating sphere, and he failed at that time just to describe it this way. Now we know why, and anyway, it is a very useful concept, as I'm going to show in a minute. So we have to look what kind of instabilities and transition to quantum turbulence appear in high-Stokes flow of helium-2. And as I said, we are at two-fluid regime above 1 Kelvin. So the helium displays the two-fluid behavior. We believe that we are to consider just the isothermal flow. So if there are no quantized vortices, we have two independent velocity fields, and instability can occur in either of them, either in the normal fluid or in the superfluid. In the normal fluid, the instability will be governed just by approaching this critical Donnelly number. So the drag coefficient should increase there. But in the superfluid, actually the transition to turbulence in the superfluid will be governed by what is called Donnelly-Glabresson instability and depends on velocity. So the question is which instability occurs first and whether a crossover from one to the other is experimentally possible to observe. And here is the answer. You know, this is just the experimental data using the oscillating fork. And you can oscillate the fork either with the fundamental mode, which is right here, or with the overtone, which is like here. And the results are basically the same. And you see, if you plot the drag coefficient here as a function of the Donnelly number, everything nicely collapses if you are in the laminar flow. So the superfluid component does not contribute with anything just by the increase in the effective mass. But then if you reach the critical Donnelly number, there is just departure from this nice law, and that's where instability in the normal fluid occurs first. On the other hand, if you plot the same data as a function of peak velocity, you see that there is no clear transition here, but if you go to very, very high velocities of the order of several meters per second, as you can see, then everything collapses here because due to interaction, mutual friction between quantized vortices and a normal fluid, everything appears as a single fluid, and we have just the behavior as in classical liquids. So at high velocities, helium behaves as a single component fluid, and at low velocities, classical likes universal scaling is observed. And actually, with certain sizes of the fork, you can see this crossover. So below certain temperature, in this case it was 1.10 Kelvin, we observed the Donnelly-Glabresson instability. At low temperature, everything collapsed here. But above this temperature, everything was due to classical light instability. So we see that crossover between Donnelly-Glabresson instabilities and just classical like instability can be observed. And it can be observed not only in this case of oscillating forks or oscillating objects, but it can be also observed in a transition to quantum turbulence in oscillatory thermal counterflow. oscillatory thermal counterflow. What is it? It is nothing else but the second sound. And this second sound can be just generated either mechanically, as it was done first by Kotzebue and Swift long time ago. And you see that this is the resonator right here, and this is the super leak. So there are bellows, and these bellows, because helium is compressible, they can push in the superfluid component. So there is a counterflow here, and they observe the transition to quantum turbulence. Or you can do it thermally. You can have a heater on one side of the resonator and a thermometer on the other side, and you can do it as it was done, for example, by Tim Chagovec here in Prague in 2016. And the sign of transition to quantum turbulence is that if you increase the drive, these Lorentzians, they suddenly start to have flat tops, because actually the amplitude cannot go down because you create quantized vorticity. And if you go to even higher drives, so the flat top will just stay there. So we decided at the time to improve the results a little bit. And we just had an experiment in which just we had the same resonator, but on the top of what I already said, we have also the second sound, which was generated across the channel. And that was there just because we wanted to probe what is the vortex line density there. And as I said, with this heater, we can generate second sound, either the first harmonic, the fundamental, or the second harmonic or third harmonic. And with this second sound, we have seen that while in the first harmonic, we have observed quantum turbulence here, with the second harmonic, we have seen hardly nothing, because there is a node and the quantum turbulence occurred exactly in the place where the antinode of the second sound appeared. So this was interesting, and we just started to investigate that a little bit more. And we went back to the work of Vinen and Kolmogorov, who actually claimed that in the case of these nice experiments of Skrbek's group, where they oscillated a little sphere up and down, so they observed the critical velocity, which was described by just this critical velocity due to Donnelly-Glaberson instability. But actually, for the experiment of Kotzebue and Swift and for our experiments, it didn't work. So we actually thought, okay, maybe it's possible that we employ just the same approach, and we just ask whether the instability can happen in the normal component. Enough, it was the case, but the opposite. While in the oscillating objects, the first instability occurred in low temperatures, here, it's the opposite is true. So the crossover occurs here as well, but in opposite sense with temperature. So that's an interesting result. So now maybe I can mention a few characteristics of 3D quantum turbulence at finite temperature. I don't have much time, but I mean, the first, of course, is just the quantum turbulence in superfluid helium 3b at finite temperature, where the normal fluid is so viscous that actually it doesn't move. And I mean, it serves as a background. So there, everything is slightly different. And if for classical flow, you describe everything using Navier-Stokes equation, in this case, the superfluid flow is described by different equation, which you obtain from the Euler equation by coarse graining it over distance, which is much larger than quantum length scale. And if you do that, you, for example, figure out that eddies larger than certain maximum size cannot exist. And as it was shown by these authors, by Lvov, Nazarenko, and Grisha-Volovic, and independently by Joe Winen, the energy spectrum is quite peculiar, and everything is different than we are used to. But what we did in Prague was just to characterize the quantum turbulence in pipe flows. And we did that by investigating using the second sound and sensitive thermometry. The beauty of it is that in the same channel, you can create different kind of flows. You can create counterflow if you have a heater here. You can create superflow if you have super leaks here and there, so only the superfluid can go through and make a through flow through this channel. Or you can have a grid or just some kind of honeycomb, and you can have a co-flow. And actually, the difference between counterflow and co-flow is quite striking. So you see, if for classical flow, for the co-flow, you see like here, depending on, it doesn't depend on the temperature. So there are many temperatures and many kind of experimental data, but they actually do not depend on temperature. And vortex line density scales as velocity in the power 3/2. In counterflow, it is completely different, and the scaling is like v squared. So that's a message to take home, that co-flow and counterflow, they just scale completely different. And if you look at the decay, that's even bigger kind of puzzle, because all of these flows, if you start with high enough vortex line density, they decay as T2 minus 3/2, classically like. So even the Oregon Toadgate experiment, the co-flow in Prague, and counterflow, which was measured in Prague, they all of them in the long time decay as T2 minus 3/2. And from this expression, we can even extract just effective kinematic viscosity. So that's a puzzle which needs to be somehow investigated. And again, I can do that if you just consider what's going on from the point of view of the superfluid energy spectrum. In a pipe flow, for example, if you start very gently, so you drive at the length scale, which is similar to that of the size of the group. So that's why in the beginning, there is no experimental data, but the decay should be like 1/t. And if you do that experimentally at higher drives, so the beginning of the decay, there is this quantum peak, is consistent with 1/t decay for a little while. And for later times, the decay is consistent with T2 minus 3/2, which is kind of classical like decay. But the energy spectrum is quite different in the case if you drive everything steadily. Why? Because there is no Kolmogorov Kolmogorov scale. Why? Because there is mutual friction, which operates at all scales, and there is a dissipation of energy at all scales. So it goes steeply down, and there is only this quantum peak there. But if you stop driving, then this energy, which sits here, goes through Richardson cascade, and then eventually everything starts to decay as in classical case. And maybe I can mention that also the intermittency, which is important characteristic of three-dimensional turbulence, depends on temperature, as it was predicted by Victor Wolf and co-authors, and recently by Rahul Pandit confirmed numerically. And in our experiments, it was seen that indeed at temperatures about 1.9 K, the intermittency is the largest. It is always stated, and often stated at least, that if you generally drive turbulence, quantum turbulence by mechanical means, that it is of the Kolmogorov form. Is that true? Well, no. Experimental answer from Prague is quite clear, because what we had was we had a fork, and this fork was oscillating in between the second sound sensors. So we have been able to measure simultaneously the drag because of the fork and also the vortex line density. And we can measure the decay of vortex line density. And we have seen clearly that the decay of that vortex line density was the same as in Vinen-like turbulence. Why was that? Because in this case, we had a very, very small fork, small in that the cross-section of prongs was about less than 100 microns. And the vortex line density was such that the mean intervortex distance was of the same order. So you actually drive the Vinen turbulence, and it definitely then consequently decays as a Vinen turbulence. As for thermal counterflow, the situation is even more complicated. So as we know, everything depends and has been explained phenomenologically by Joe Vinen based on this equation, which bears its name as Vinen equation. And if you just look at this equation and would like to see which way the quantum turbulence, the vortex line density should decay. It should go like 1 over t. But in numerous experiments, it was shown that it is not true. But again, we can understand that. If you drive it very, very gently, then even the counterflow experiments goes and decays as 1 over t. That it is seen just in this set of data here. But if you drive it more vigorously, then you just drive not only the quantum turbulence at very small length scale, but you also drive, because of the normal fluid flow, the classical like turbulence at the size of the channel. And because of the mutual friction, it actually starts to develop the classical like Kolmogorov spectrum. And then the decay should gradually become of the classical type, which even it's true. And maybe only a few words about our new experiments, because I just explained that in classical channel counterflow, the situation is complicated because you have to take into account the friction because of the walls. So what we need is an unbounded flow, not in a channel, but say you have point-line Heeker and the spherical counterflow looks like this. And they have been interesting numerical studies. It started with Emil Varga here in Prague in 2019, and then continued with just the work of our Japanese colleagues in the group of Makoto Tsubota. And we performed the experiment in Prague. So we have a spherical cell, which is about 2 centimeters in diameter, and there are second sound sensors here. There is a heater in the middle, and we just can measure the vortex line density inside. But this is tricky experiment because actually, because of this geometry, spherical geometry, the normal modes of second sound are not simple. I mean, you have to express everything in terms of spherical harmonics, and it's rather a complicated business. You can read the details in our paper, which will appear soon in Phys Review Fluids. And the result is that fine, we can measure that. But there have been previous work of our host, Andrew Bagali, together with Carlo Barenghi and group in Newcastle, and they have shown that actually it is impossible to reach steady state of spherical counterflow unless there is a temperature gradient. So we asked that question experimentally, is there any temperature gradient? And there is not a complicated experiment. It's pretty straightforward. You have the heater and you have small thermometers, and you simply move these thermometers in the vicinity of that heater. It is not easy to do it exactly. We had a special stepper motor for that. But then you see the quality of the data is not perfect, but clearly you can see that if you go close to the heater, so that there is a temperature gradient, which is roughly that as it predicted because of the simple model. So yes, the temperature gradient is there and it's inevitable. But even kind of bigger surprise was that we started to measure the vortex line density, or better, we just described that in terms of inverse quality factor. And you can see that in the beginning, there is what you expect. The vortex line density is proportional to the counterflow velocity square. But then something strange happens, and depends where you measure, whether actually doesn't depend on which frequency you measure, whether it's low harmonics or much higher harmonics. You can see these plateaus there. And even more strange result is that these plateaus, if you calculate the Dunley number, which I just introduced a few minutes ago, it's about 50. The beginning of this plateau, independently of the temperature, just occurs there. So we believe that the onset of the plateau is just connected with the onset of classical turbulence in the normal fluid in the vicinity of the heater. So it's completely different and the opposite way than what has been shown by, say, Jim Taff and co-workers in the case of classical channel counterflow. There are also 2 stages. I mean, there is T1 and T2 stages of superfluid turbulence in the counterflow, T1 and T2, but then the vortex line density goes up, which means that the normal fluid actually drives the vortex line density. Here the opposite is true. So the superfluid actually drives the normal fluid, and the plateau just occurs because of that. And not only that, we also have been able to measure the decay of this quantum turbulence, and we can see that the late decay is actually consistent with 1/T, which is signature of Vinen turbulence. So the characteristics of the spherical symmetric counterflow are that there is a plateau which is observed, that it is fundamentally different from channel counterflow. So the superfluid feeds the normal fluid here, and it behaves as unbounded flow driven at small scales. And the vortex line density decays as 1/T, which is a proof that we deal with Vinen type of turbulence. And as I said, you can read soon the details in this publication. And I think my time is over, so I will leave you with this summary here, and I would like to thank you very much for your attention.
Thanks very much, Ladik, for
Uh-huh.
Ooh, there was a bit of a noise there. For a really interesting talk. So, does anyone have any questions? Either pop your hand up and unmute yourself and ask them, or pop something in the chat and I can read it out. Samuli.
Yes, thanks for a very nice talk.
Thank you.
I was going to ask you about you made this comment that the intrinsic quantum turbulence creation mechanism is more difficult to experimentally observe than the extrinsic one. Is there theoretical understanding of the what kind of velocities are needed and how that may depend on parameters?
I can tell you first what are the experimental values. So it is believed that, for example, Avenel and Varocco, they measured what is now understood as intrinsic vortex nucleation. It was in a flow through very, very tiny orifice. And they have been able to see intrinsic vortex nucleation at critical velocities of the order of 10 meters per second and even higher. Another group who actually managed to prepare a sample of helium-2 without quantized vorticity, without remnant vortices, it was the group of Hideo Yano in Osaka. So they did it in such a way that they had a special chamber with very small orifice, and then this channel was filled from just the helium bath very, very slowly. And because of that, they have been able to see very, very high velocities of oscillating wire without just generating quantized vorticity. So everything was laminar. But as soon as you had some quantized vortex which sat on that wire, they observed extrinsic vortex nucleation. So these experiments are all described in the book. So if you are interested, you may see that. But I mean, generally speaking, in a helium-2, in macroscopic flows, more or less in all of them, the critical velocity for generating of quantum turbulence is of order of 1 centimeter per second, 2 centimeters per second, or half a centimeter per second, but it doesn't spread by more than order of magnitude, which is interesting. And I think that this is because we have to deal with extrinsic vortex nucleation and with the surface and with quantized vorticity, which is remnant in there. And in this respect, all these experiments are more or less similar. So in practice, unless you take very, very special care, the critical velocity for quantum turbulence is of the order of 1 centimeters per second. But if you are very careful and you prepare the sample in a special way, you can go up to 10 meters per second, and you may talk about intrinsic vortex nucleation. That's for helium-4. In the case of helium-3b, so here probably Volodya also knows more about that. I participated in these experiments only a little bit, but if you take great care and if you prepare the vessel with a special care, for example, with out of quartz, then in helium-3b, you can have a sample of 3 helium-B, which is free of vortices, and you can observe both intrinsic and extrinsic vortex nucleation. Does that answer your question?
Yeah, thank you.
Any other questions? If not, let's thank Ladik again.
Thank you very much for your attention.
And I will advertise that the next talk is in a couple of weeks' time. It's on the 30th, and it'll be given by Seth Musa, who's a PhD student at MIT, and a title and an abstract will be circulated to the mailing list. So hope to see you then.